Now we have to study. So what is the rings? New chapter here. So what is a ring? What is the definition of rings? So in the last lectures, we study what is a group theory, and in this lecture we have to going to study here what is a ring. So what is the definition of a ring? So definition: a non-empty set R. Non-empty set R with the binary operation addition and multiplication, denoted by addition and multiplication respectively. Satisfying. So some axioms here is said to be a ring, is said to be a ring if the following axioms are satisfied. If the following axioms are satisfied. So axiom 1. So what is axiom 1? So R plus is an abelian group. Next properties. So that is next axiom. Second axiom is multiplication is associative. Multiplication is associative. So what is that is A into B. Multiplication is there. A into B into C is equal to A into BC. For all ABC are the elements of the set, non-empty set R. So then third property is the operation multiplication, the operation dot, so that is the multiplication, is distributive over addition, So that is A into, what is the distributive property here? A into B plus C is equal to A into B plus A into C for all A, B, C belongs to R. So A, B, C are the elements of R. Or simply B plus C, so into A, so that is B into A plus C into A. Okay. So this is the left distribution law and this is the right distribution law here. So for all A, B, C belongs to R. If set R, if a non-empty set R with the operations, binary operations plus and multiplication dot, satisfying the following axioms. So what is the axioms here? R plus is an abelian group. Okay. So what is the abelian group? So R plus is a group with commutative property. Then R plus is an abelian group. If this property is satisfied, and what is the multiplication is associative. Here addition is associative in group. What are the axioms in group? So closure property, associativity with respect to addition, existence of identity, existence of inverse, and commutative property, then R plus is an abelian group. R plus is an abelian group. Then what is the multiplication is associative. So AB into C is equal to A into BC with respect to multiplication operation. So if this axiom is satisfied, also the operation dot multiplication is a distributive over addition. So this is the left distributive law. So this is the right distributive law. If these axioms are satisfied by the set R with respect to plus and multiplication, then R is said to be a ring. Very simple definition. Simply three conditions extra there in consideration of definition of a group here. So this is the ring here. So it is denoted by. So R ring R is denoted by R, simply R plus dot. These are the binary operations, or simply, so these are the notations here, R plus dot. Okay, so this is the definition of a ring here. Okay, so what is the theorem? What is the theorem on a ring? So we have to prove here some properties on a ring. Very simple properties are there, and then we have to taking the examples on a ring. Okay, so what is the theorem? Theorem here, in a ring R, the following results holds. The following results holds. So what are the results here? So result 1. So that is A into 0 is equal to 0 into A is equal to 0. Okay, for all A belongs to R, where R is the ring here. Okay. What is the second result here? So that is A into minus B is equal to minus A into B is equal to minus AB. Minus AB for all AB belongs to R. AB belongs to R. Then next result. Third result. So what is third result? Minus A into minus B. Minus A into minus B is equal to A into B here. Okay. For all AB belongs to R. So what is the next result? Fourth result here. So A into B minus C, so is equal to A into B minus A into C. Okay, for all A, B, C are the elements from the set, non-empty set R here. If R is a ring, then prove that these results here. So what is the proof? So that is result 1. Okay. So what is the result 1? A into 0 is equal to 0 into A is equal to 0 for all A belongs to R. So for any element of R, so that is A belongs to R, so that is A into 0 is equal to, so let us consider A into 0 here. So this can be written as A into 0 plus 0. A into, so 0 can be written as 0 plus 0 here. Okay. So then, what is the distributive property here? So this can be written as, so A into B plus C is equal to A into B plus A into C. That is, so what is the property here? A into distributive law. Since A into B plus C, just in we study here in the definition of a ring. So A into B plus C is equal to A into B plus A into C. So this is a distributive law here, left distribution law here. By using this law, so this can be written as A into 0, so is equal to A into 0 by using this law here. So this can be written as, A into 0 plus 0. Because 0 is the identity element here, so this can be written as this, like that. Okay, so A into 0 plus A into 0. So this can be written as also, so A into 0, 0 is equal to A into 0. So this is a left cancellation. So that is left cancellation. Left cancellation. So we get here, so this implies that A into 0 is equal to 0. A into 0 is equal to 0. So that is A into 0 is equal to 0. Very simple here. So we write here B 0 plus A, 0 is equal to 0 plus 0. Then by using distributive law, so that is left distribution law, A into 0 plus A into 0. Then we left hand side A into 0 plus 0, and then left cancellation we get the result here. Similarly, we prove very simple. So that is 0 into also similarly. So that is what happened, 0 into A is equal to 0. So this implies that, so A into 0 is equal to 0 into A is equal to 0. So that this first result is proved here. Okay. So very simple result here. So what is the second result? So result 2. Result 2. So A into minus B is equal to minus A into B is equal to minus AB for all AB belongs to here. So now we prove here the second result here. So for any element of the set R, so R is the ring here. So that is what happens. So A into 0 is equal to 0. So first result. So we already proved that result. So this can be written as A into, so 0 can be written as minus B plus B is equal to 0, because R is a ring, R plus is a group. So what is the property here? So this is the existence of inverse property, because R is a group also with respect to addition operation, plus operation. So we can write 0 is equal to minus B plus B is equal to 0 here. So this can be written as A into minus B plus A into B. So that is equal to 0. Why? So this is a left distributive law. By definition of, so this is distributive law. Left distributive law. Left distributive law. Okay? So this implies that what happened? So this implies that A into minus B is equal to minus AB. A into minus B is equal to, so A into minus B is equal to minus AB. Similarly, we prove that, similarly, minus A into B is equal to minus AB. Same, we prove directly. So minus A into B is equal to minus AB. So from these two, we get the second result here. So that is A into minus B is equal to minus A into B is equal to minus AB. Hence the result here. For all AB belongs to R. So hence the second result. What is the second result? A into minus B is equal to minus A into B is equal to minus AB. The result is proved here. So very simple results are there. So what is the next result? What is the next result? So what is the third result here? So minus A into minus B is equal to AB. So for AB are the elements of the set R, AB and R is the ring. So we have. So what happened here? So minus A into minus B is equal to minus A into minus B is equal to what happened here? So minus A into minus B. Since what happened here? So we prove here minus A into minus B is equal to A into B. So we prove now here the result 3 here. So minus A into minus B is equal to minus A into minus B because of result 2. Because of result 2. So what happened here? So that is A into minus B is minus AB. So we write here, so minus A into minus B is equal to minus A into minus B. So result 2 here. Since result 2. Okay. So this can be written as, so this is equal to, again we write this. By result 2, by using this result, again we write it. What happened here? So minus. So A into minus B. A into minus B is minus AB. So minus AB. And this is equal to what? So AB. This is equal to A into B. A into B. Okay. So minus A into minus B is equal to A into B. Hence the result. So that is, this implies that. So minus A. So this implies that here. Minus A into minus B is equal to A into B for all A, B belongs to R. Here the result 3rd is proved here. So this is since result 2 here. Result 2 here. So this is, these proofs are very simple here. So now we prove the last result. A into B minus C is equal to A into B minus A into C. So we always study here A into B plus C is the distributive law, but sign is minus here. So A into B minus C is equal to A into B minus A into C for all A, B, C belongs to R. So what is the result 4? Result 4. So what is the result 4 here? For ABC, for any ABC from the set R, elements from the set R. So what happened here? So A into B minus C. A into B minus C. So this can be written as A into B plus minus C. A into B plus minus C. B minus B, C can be written as B plus minus C. Then by distributive, what is the distributive law? So we know what is the distributive law. So that is A into B plus C. So the left distribution law here. So that is A into B plus A into C. So this is distributive law in the definition of a ring R. So then A into B plus minus C. This can be written as by using this distributive law. So that is A into B plus A into minus C. Okay. A into B plus A into minus C. But what is A into minus C? By using result 2 here. So A into minus B is equal to minus AB. So what happened here? So A into minus C. A into minus C is equal to minus AC. So A into B minus A into C here. By result, since result 2. Result 2 here. Okay. Therefore, what happened here? So that is A into B minus C is equal to A into B minus A into C for all A, B, C belongs to R. And the result 4 is proved here. Okay. So we prove the theorem. Very simple results are there, and we prove the results on a ring R. Very simple results. Some basic results are there. Okay. So we take an example. Example. show that the set Z7, so that is 0, 1, 2, 3, 4, 5, 6 forms a commutative ring, with unity under addition and multiplication operation. So show that the set is Z7. So what is the set Z7? So 0, 1, 2, 3, 4, 5, 6 are the elements of this set here. So 7 elements are there in the set Z7. So how to obtain this set here Z? So we dividing any number. We dividing any number by 7. If 7 is there, number 7, if 1 is there, 1 is number, 0 is number, 0 divided by 7, then the remainder is 0 here. If 1 divided by 7, then the 1 divided by 7, then the remainder is 1. 2 divided by 7, then the remainder is 2. And so on. 6 divided by 7, then the remainder is 6. Again, these numbers are repeated. So this is the Z7 set here. So prove that the Z7 is the ring under the addition and multiplication operations. So what are the addition and multiplication operations here? So what is the solution? So show that this set is a ring. Let Z7 is the set like that 0, 1, 2, 3, 4, 5, 6. Okay. So what is the closure property? So first we prove that Z7 is ring. So for that proving Z7 plus is a commutative group. Then associative with respect to the multiplication operation and a addition distributive over multiplication. So those three properties are satisfied, then the set is a ring. So we prove here. So what is the closure property? Closure property. So this is a property in a group. So closure property. If we take two elements of this set here, so 5 plus 5 addition plus 7 modulo 4 is equal to what? So that is 2 here and 3, 4. So that is a 5 here. Okay, that is a 5. So what is the definition of addition modulo and this is a multiplication modulo? So these are the operations here. So this is the plus addition modulo 7 and this is the multiplication modulo 7 here. So this is the addition and multiplication operations here. Okay. So we prove here the closure property. So what is the 5 plus addition modulo 7 4 is equal to how it is? So that is a 5 plus 4, that is a 9. So 9 divided by 7. So remainder is 2 here. Remainder is 2. 5 plus 4. What is the definition of addition modulo? So we are already studying the group theory here. What is addition modulo 7 and multiplication modulo 7. Okay. So that is 5 plus 4, that is 9. 9 divided by 7. Then 9 divided by 7. Then remainder is, what is R? What is R? So remainder is 2 here. sorry, remainder. Remainder R is 2 here. So 5 and 4 are the members of this set. So 2 is also members of this set. So closure property holds here. So similarly, 3 multiplication modulo 7, 4. Multiplication modulo 7, 4. So that is 3 into 4. So that is 12. Then divided by 7. Divided by 7. So 7 1 the 7. Then remainder R is 5. Remainder R. So 5 is also member of this. So 3, 4 are the members of this. 5 is also members of this. So therefore, closure property holds here. Okay, closure property holds here. Okay. So under these operations, Z7 satisfy the closure property. The closure property. Okay. Then what is the next property? So then it is easy to obtain the existence of identity with respect to addition operation, existence of inverse with respect to multiplication operation. Okay. Then associated with respect to addition. So these are very simple to prove that this property. Then we can directly say here Z7 plus is a group. Z plus 7 is a group. So what is the identity here? So what is the identity? So what is the identity element there? So that is the 5. Addition modulo 7, 0. So this is what? 5 plus 0. 5 plus 0. 5 plus 0 is 5. So divided by 7. So the remainder R is 5 here. So that is 5. That is a 5. Okay. With respect to addition modulo. So again what is the 5 plus multiplication modulo 7. 5 multiplication modulo 7 to 1. So what is this? That is 5. So because 5 into 1. So that is 5. Divided by 7. So what is the remainder? R is 5 here. So what is this? So here 0 is the additive identity. And what is 1 is the 1 is the multiplicative identity. Multiplicative identity. Okay. So identity exists in this set here R. Okay. So that is what is the existence of inverse. Existence of inverse. So what is the existence of inverse here? So we take elements 4 from this set here. 4. Again, we take element 3 here. So what is 4 plus 3? 4 plus 3 is what here? 7. 7 divided by 7. 7 divided by 7 is 1 and remainder is 0. R is 0 here. So this is equal to 0. This is equal to 0. Similarly, what happened here? So that is 3. So what is this? So then what happened here? So that is 4 is the inverse of 4 because 0 is the additive identity here. Therefore, the element 4 is the inverse of 3. 4 is the inverse of 3 because 4 addition modulo 7 3 is 0. 0 is the identity element. Then 4 is the inverse of 3. The element 4 is the inverse of 3. Similarly, 3 is the inverse of 4. 4 is the inverse of 3 and 3 is the inverse of 4 here. Okay, so this is very simple here. Then we also prove here commutative property. Commutativity. Commutativity. So what is the commutativity property? So that is 4 addition modulo 7 3. So that is 4 plus 3 7. 7 divided by 7. That is 1. Remainder is 0. So that is 0. So this equal to 3 plus addition modulo 7 3 4. So this is also 0. So this is also 0. Therefore 4 addition modulo 3 is equal to 3 addition modulo 7. So that is 4 addition modulo 7 3 is equal to 3 addition modulo 7 4. So this equal to this. So this is the commutative property holds there. 3 and 4 are the elements of the set R. Therefore commutative property holds here. Therefore R plus E R7 Z7 is a abelian group. Abelian group, okay? Because Z7 plus is a group with commutative property. Therefore Z7 plus is a abelian group here. So further we prove that easily. Further we prove the associativity with respect to multiplication, with respect to multiplication operation, this and distributive property. Distributive property. So this is very simple here. You take any 3 elements, then it is very simple with respect to multiplication operation. For example, something 4 dot 7, so 3 dot 7 multiplication operation, something 5 is equal to, so that is 4 multiplication modulo 3 is equal multiplication modulo 5. So we can easily show that this. So you know the definitions, then you can easily show here the associative property and distributive property. Therefore Z7 is a ring because Z7 plus is a abelian group satisfying associative property and distributive property.